Hi everyone, welcome to another lecture on ETAP. On this session, we are going to discuss about types of electrical loads and its demonstration on ETAP. There are three different types of electrical loads, namely constant power load, constant current load, and constant impedance load. Constant power load, that means at any instant load consumes constant power irrespective of the changes in the voltage. Example, motor type of loads. Constant current load, as its name implies that at any instant load draw constant current irrespective of the voltage change. Power electronic devices are the better example for this category. I can also add few examples like variable frequency drive, UPS, where even power electronic devices are included. Constant impedance load. At any instant, load maintains constant impedance irrespective of the voltage level. That means, in order to maintain impedance constant, if voltage increases, current also increases. Our voltage decreases, current also decreases. Heaters, electric arc furnace are the better example for constant impedance load. Let us understand this electrical loads in terms of voltage and current relationship. Let me take down constant current load. Have a look at this. Irrespective of the voltage change, current remains constant. So in this category, if the voltage increases, our power drawn from the supply increases since current is constant. Then coming to constant power load, this one, if the voltage increases, current decreases so that power is maintained constant. If the voltage decreases, current increases, in that way also power is maintained constant. Then the third one, constant impedance load. In the case of constant impedance load, when the voltage increases, current is also increases. Or in other words, voltage decreases, current decreases such that impedance can be maintained constant. So I have given the equation to relate all the three cases. In fact, if you want to find out power at the voltage, given voltage V, we have to use this formula, Pi into V by Vi whole power K, where Pi and Vi are nominal power and nominal voltage, or in other words, Pi is nominal power at nominal voltage of Vi, where P is power at a voltage of V. Okay. Here K value is 0 for constant power load. 0 means this net factor becomes 1, so P becomes Pi, that is constant power load. Then for constant current load, this K value becomes 1, that means your power at voltage V is Pi times of V by Vi. Then for constant impedance load, K is 2, that means your power at voltage V is Pi times of V by Vi whole square. Let me discuss few examples. A 1 kilowatt constant impedance load is fed from voltage source of 0.9 per unit. What is the power consumption? So it is constant impedance load. We have to take down the same formula, whatever I have mentioned over there. Use K is equal to 2. That means what is your Vi? Vi is your nominal voltage. Nominal voltage is 1 per unit. What is Pi value? Pi value is 1 kilowatt. For the corresponding nominal voltage, what is the load? 1 kilowatt. So 1 kilowatt Vi is 1. What is this V value? V value is 0.9. For this V value only we are calculating power P. So use this formula and find out power as 0.81 kilowatt. Because voltage is reduced to 0.9 from 1 per unit, In the same proportion, current is also reduced in order to maintain impedance load. If V and I is reduced, look at your power. Power is also reduced, not 1 kilowatt. Instead of that, you are getting 0.81 kilowatt. Then coming to constant current load. The same problem, but only change is constant current load. So use same equation, but only change here you can observe is K value is 1. If this K value is 1, then you may get power as 0.9 kilowatt. Since this is constant current load, current remains same. However, voltage is reduced by 0.1 per unit, and so as power is also reduced by 0.1. That is what 0.9 kilowatt. And the third case is constant power load. That means we do not want to use any formula. Straight away we can say whatever may be the voltage value, the power remains same, 1 kilowatt. It doesn't matter 1 per unit voltage or 0.9 per unit voltage or 0.8 per unit voltage, your power remains same. Even you can use the formula and cross verify this answer. Let's move on to ETAP and demonstrate these things. Let me demonstrate constant power load initially. Take a grid, a bus and a lumped node. Connect these three components. Take grid voltage as 11 kV. Lumped load value as 1 kilowatt. Let me assume constant power load, so 100% kVA, then 1 kilowatt with 100% power factor. Now run load flow. Actually it is 11 kV system. I want to showcase what is the power taken by this load. Here you can see 1 kilowatt. For 1 per unit, that is 100% voltage, it is taking 1 kilowatt. I'll also hint that one here. Constant power with 1 per unit, or even I can say with 11 kV, the power drawn by the load is 1 kilowatt. Now let me showcase the same SLD with 0.9 per unit. 0.9 into 11 becomes 9.9. So for this voltage, what would be the power drawn by the load? Go to grid voltage, make it as 9.9. That is 0.9 per unit. Now run load flow. Now you can see the answer. In both occasions, power drawn by the load is 1 kilowatt. I'll also give the hint here. Load consume 1 kilowatt of power irrespective of the change in the voltage level. It doesn't matter 11 kV or 9.9 kV, the load continue to take 1 kilowatt of power. That means if the voltage level is less, current is increases to compensate the required power. This is what you can observe from this. Now let's move on to constant impedance load. Copy the same SLD. Select the load and make a necessary change. That is constant impedance load, 100% constant impedance load. Run this model and you could see here 1 kilowatt is a power drawn by the load because 11 kV, that is 1 per unit, is a supply voltage. Now I copy this and paste it again in order to have response for 0.9 per unit. Make a change on the grid, 9.99 kV. Run this model again. Now look at the load power. On 11 kV, the load power is 1 kilowatt, 0.9 per unit, that is 9.9 kV, the load power is 0.81 kilowatt. So this is what we observed on the hand calculation. If you want to see the current, look at the current difference here, 0.052 for 11 kV and 0.047 for 9.9 kV. That represents whenever voltage decreases, current also decreases in order to maintain impedance constant. Or in other words, whenever voltage increases, current is also increases to maintain impedance constant. Let's move on to constant current load. First you make a label. Initially let's go with 1 per unit, that is 11 kV. Copy and paste the same SLD. Select the load and this time we have to choose model type, polynomial. There are P1, P2, P3, 3 values. These represents percentage of that constant current, constant impedance and constant power value. Say for example, I am going with P2 as 1. Where P1 is a constant impedance and P3 probably constant power. Now run this one. You could observe here current drawn by the load is 0.052. Let me copy and paste the same model with 0.9 per unit. Make a change here, 0.9 per unit and 9.9 kV on the label, and also in a grid voltage. (9.9 kV on a grid voltage). Run the load flow. It's a constant current load. Look at the current drawn by both loads. In fact, with 11 kV, 0.052 and the same value when we go for 9.9 kV. Also have a look at the power drawn by the load. 1 kilowatt for 11 kV and 0.9 kilowatt for 9.9 kV. That means in order to maintain current constant, when the voltage is decreased, impedance is also decreased, such that power is decreased. Or in other words, if the voltage increases, impedance also increases in order to maintain current. In that case, power increases. In a conclusion, constant power load always draw constant power irrespective of the change in the voltage. Constant impedance load will maintain constant impedance by changing voltage and current, and constant current load always draw a constant current irrespective of a change in voltage. Finally, let us have one more problem. A 1 kilowatt load consists of 50% of constant impedance load, 25% of constant current load, and 25% of constant power, which is fed from 0.9 per unit voltage source. What is the power consumption? While solving the solution for this problem, you are supposed to take account of all the three cases, where the first term representing your constant impedance load, second term representing your constant current, and the third term representing your constant power load. So where A, B, C represents the percentage of those loads. In fact, this A, B, C, all these three put together 100%. Or in other words, I can tell you it is 1 per unit. Now substitute your total load 1 kilowatt as PI. That is your PI for VI. What is VI value? 1 per unit. So wherever I have VA, I just substitute 1 per unit. Wherever I have PI, I substitute 1 kilowatt. Then for 0.9 per unit, what is the power consumption? You substitute V as 0.9 wherever it is in the equation. Now this A value is depending upon the load. If it is constant impedance load, 50%, A value is 50%. The next one is constant current load, which is representing V here, that is 25%, 0.25. Then C is constant power load percentage, that is 25. Substitute it here. Then you calculate this power, you may find 0.88 kilowatt. Let me demonstrate this also in our ETAP. I go for the rating page and make it as 11 kV, and this lamp load, let me go to main PVT, make it as polynomial. We substitute here as 1 kilowatt, that is actual power. We see here this is constant impedance loading. Constant impedance loading is 0.5. Then next one is constant current load, that is 0.25. And finally constant power load, which is automatically changed to 0.25. So that 0.5 plus 0.25, 0.25 becomes 1. Now for 11 kV, what is the power taken by this load? Let me check it out. So for 11 kV, as usual, 1 kilowatt is the power drawn by this. Now let me go for the same SLD. Paste it here. Only change is rating 9.9. Now let me run this load flow. For 9.9 kV, have a look at the power drawn by the same load. It is 0.88 kilowatt. This is the answer what we observed in the earlier problem, 0.88 kilowatt. So have a look at the load, 1 kilowatt load, 50% constant impedance, 25% constant current, and 25% constant power. So for this category, if the voltage is 1 per unit, the load consumes 1 kilowatt. On the other hand, if the voltage is 0.9 per unit, the load consumes only 0.88 kilowatt. I hope you understand the different types of electrical load and its simulation in ETAP. For more update, subscribe my channel. Thank you.